In this session, we're going to talk about thermochemistry. Now, what is thermochemistry? To put it in simple terms, thermochemistry is just, the chemistry that has to do with heat, because the word thermo means heat. Now, what is heat? We say heat is defined as, just a form of energy. Now, if heat is a form of energy, then what is energy? Energy will be the capacity to do work. Then what is work? Work is defined by when you multiply your force multiplied by your distance, then you've done work. When you apply your force over a certain distance, then you've done your work. And we can manipulate this equation by saying F, your force, your pressure is equals to force over area. So your force in this case will be pressure multiplied by area, like that. So you can say P multiplied by A multiplied by D. Then you know that your area multiplied by your distance, that is your volume. So work done can also be found as your pressure multiplied by your change in volume, like that. Okay, now we've talked about energy, and energy being the capacity to do work. Now there's what is called the first law of thermodynamics. Now this law states that energy can neither be created nor destroyed, but this energy can be converted from one form to another. Now what is this thermodynamics? So thermodynamics, is just a study of energy and its conversions. We're talking about thermodynamics here. Okay, now we're talking about energy being, undergo this, conversions from one form to another. It's neither created, it's neither destroyed, but it's just converted from one form to another. Now there are certain, there are different kinds of energies. Examples that I can give, there's what is called thermal energy. You can talk about thermal energy. You can talk about this chemical energy. There's nuclear energy. There's electrical energy. There's potential energy. There's also kinetic energy. Now, and other forms of energies. They're different, there are a lot of them. Now, what is thermal energy? This is just the energy which is associated with the random motion of atoms. Let's say you're hitting, probably something, then those atoms tends to move around randomly. We call that thermal energy. Then the chemical energy, in this case, we're just talking about the energy that is stored within bonds of chemical substances. Okay, is either between in a single bond and a double bond. That energy that is stored within the bonds of chemical substances. Then nuclear energy, we're just talking about the energy that is stored within the neutrons, and the protons, like that, in an atom, like that. Then electrical energy, we're just talking about the energy that is associated with the flow of protons or electrons. The flow of electrons, probably from the negative terminal of the battery to the positive terminal of the battery, like that. Then potential energy, we just know this is the energy of position. Okay. Then kinetic energy, in this case, I'll just call it the energy of movement. Okay. These are some of the energies that you need to understand. Then, if we combine kinetic energy plus potential energy, this will give us what we call internal energy. Okay, internal energy. So internal energy is just the sum of the kinetic energy and the potential energy of all the particles in a system. We'll talk about what a system is. Now, how do you find this internal energy? So your internal energy, we say your change in internal energy or energy will be equals to, your Q plus your W like that. Okay, your Q plus your W. In this case, your Q is just your heat, and your W is just your work done. Then what are we talking about? So we're talking about a system and the surrounding. Okay, so we'll explain about those concepts later. So let's talk about the language of thermodynamics. Okay, yes, so there's what they call a system. Now this one is a thermodynamic system. It's not any other system, but a thermodynamic system. So what is this thermodynamic system? It is that part of the universe that is under consideration. Is it the experiment that you're doing in a lab? So an example that you can give on a system is an experiment in a lab. Okay, an experiment in a lab like that. So that would be a thermodynamic system. Then we've also introduced the concept of a surrounding. In this case, we're talking about a surrounding. Okay, a surrounding in this case is just everything outside the system itself, where we are, and the rest of it in the universe is the surrounding like that. Now a system can be a closed system. A system can be a closed system. A system can be an open system. A system can be an isolated system. Okay, what do we mean when we talk about a closed system? So in a closed system, we find that energy cannot be transferred between the system itself and the surrounding. Energy cannot be transferred between the system and the surrounding. Okay, but not the matter. So energy can be transferred between the system and the surrounding, but not the matter. So I find that let me give an example. Let's say this is this is a system. Okay, let me say this is a beaker. Then here there's a reaction that is going on. Now this is the surrounding, and this is the system, the reaction that is going on. So in a closed system, energy can be transferred between the system and the surrounding, but not matter. So I find that this reaction will be occurring, but the matter of this reaction is not going outside. So that is a closed system. Then an open system, let me say it's just like that. Let me say this is a beaker, and there's a reaction that is going on in here. But now you find that there is an exchange of both heat and matter with the surrounding. An example is this open beaker, or maybe a boiling kettle like that. So as this reaction is happening, some of the contents or the matter is also leaving out. So there's an exchange between the surrounding and the system itself inside like that. So this is called an open system. Then an isolated system, an example that I can give is just the vacuum flask, or let me call it a thermos flask. When you put things in a thermos flask like that, it's just isolated, like completely like that. Then let's proceed. There are also other terms that you need to understand. There's what is called an exothermic and an endothermic. Okay, an exothermic, in here we're just talking about the heat being released to the surrounding. Okay, then in an endothermic, we're just talking about the heat being absorbed from the surrounding. Okay, then another term that you also need to understand is what you call enthalpy. Okay, so like now what is enthalpy? Enthalpy is just the energy that is gained or lost during a change taking place, or during a change taking place at constant pressure. So enthalpy is denoted as H like that. And if it's a standard condition, just H, then you put this like that. So this is the enthalpy, the heat that is absorbed, the energy that is gained or lost during a change taking place. Okay, now we've talked about thermochemistry being there. Let me just say the chemistry that has to do with heat. Now there are different types of heat. Okay, in thermochemistry, there's what is called the heat of the reaction. Okay, so the heat of the reaction, this one is denoted by a change in enthalpy of a reaction. So this one is the heat of a reaction. So now you know that the reaction can either lose heat or gain heat for that reaction to occur. Let's say you've got a reaction where you've got A plus B, then this is giving us a product AB. So in this case, the heat of reaction, or the change of the heat of the reaction, will be the sum of the heats. Let me say the sum of the heats of the products, sum of the heats of the products minus the sum of the heats of the reactants, like that. Okay, so in this case, in the expression, in an expressive form, we say the change of enthalpy of a reaction will just be equals to the summation of the heat on the product side minus summation of the the enthalpy of the heat of the on the reactants, like that. So this will be our expression. Okay, then there's also what is called another type of heat that we can talk about is the heat of formation. Now, what is the heat of formation? At standard conditions, it will be in terms of the expression, we just write it the change in the enthalpy of heat of a formation. So it will just be like that. If it's a standard, you put your thing like that. So this is okay. So by definition, the heat of formation is just the heat which is either released or gained for the formation of one more of a compound. For the formation of one more of a compound. Let's say the same analogy that we used, like if we say A plus B, then this is giving us, let me say AB, like that. Now, the heat of formation in this case, how are we going to find the heat of formation? So it's just the same thing. If it's a standard, temperature or standard conditions, you put your thing like that is equals to the summation of the heat of the products minus summation of the heat of formation over the reactants, like that. Okay, now we're specifying one more for the formation. For it to form one more of this, the heat that is either lost or gained is called the heat of formation. Remember, one more. So in some questions they'll ask you, to identify if this is a heat of formation, a heat of a reaction. So you have to be able to do that. Now, this I must make mention that elements, like elements of the same molecule. Let me say O2, like that. Let me say hydrogen. These elements of the same molecule, the heat of formation of these ones is 0. The heat of formation is 0. We're saying the heat of formation of these ones, is 0, like that. Okay, now this is also true for pure elements. Probably just get oxygen, just get hydrogen, like that. This is also true. So okay, so now let's also talk about what if you get a negative heat of formation. In this case, if you get a negative heat of formation, let's say you've done your reactants and your products, but now you get a negative, let's say your heat of formation in this case is negative. Okay, now what does it mean? This means that it's just an exothermic reaction. What does it mean? Is that heat is being released. We are losing heat. It also entails that the heat of formation of these products, or the heat of formation of the products, is smaller than that of the reaction. Okay, let's talk about another heat of formation, or another type of heat. There's what is called the heat of combustion. Okay, other heats, we've got the heat of precipitation. Other heats, we've got the heat of displacement. Okay, and the heat of neutralization, there are a lot. Okay, let's just talk about these ones. So when we're talking about the heat of combustion, this is just the heat that is either released or gained when one more of a substance burns in oxygen. Combustion, you just know, is burning, right? So when that substance is either burned or broken down in the presence of oxygen, that will be called the heat of combustion. For example, when an organic substance, when they react with oxygen, they get to form mostly carbon dioxide and water. Let's say, for example, we've got your methane. Your methane is is burning in in oxygen. This will give us carbon dioxide plus water. Now we are saying one more of this compound, because it's one that is being broken. Okay, so one more of this compound is being broken. Now that heat which is required, that is required for this compound to be broken is called the heat of combustion, and this heat is just denoted as Q, like that. Okay, then there's a heat of precipitation. The heat of precipitation, in this case, we're just talking about the heat which is either gained or lost for one more of a precipitate to be formed. So we're just talking about you making a precipitate in this case. Then the heat of displacement. In the heat of displacement, we're just talking about the heat that is either released or gained for one more of an element to be displaced. Let me say you've got let me say hydrochloric acid. It's reacting with sodium in this case, and this is giving us sodium chloride. Now it means that one more of hydrogen should be displaced by sodium, okay, to form this compound, sodium chloride, or your common salt, like that. So when because this is a spectator ion and it's been displaced by the sodium, you find that sodium chloride is formed. Now one more of hydrogen that has been displaced, now the heat that is released because of one more of hydrogen being displaced is called the heat of displacement. Then other types of heats, we've got the heat of neutralization. So in here we're just talking about one more of something, so that's what you're supposed to remember, one more of something. Okay, so now let's talk about now how do you measure this heat. So the measurement of heat itself is called calorimetry. Okay, you are measuring heat. Then an instrument that we use just to measure this heat is called the calorimeter. Okay, so when you're talking about a chemical reaction, you're going to have the environment and the system, like we said. So for the reaction, the system is the reaction itself. Let's say we've got let's talk about the system and the environment. Let's say we've got a reaction in here, maybe the same analogy that we had. Let's say we have in here, we've got sodium. This is reacting with chlorine, let's say, to give sodium chloride, like that. Okay, so this reaction is what we are calling the system, because it's the one that is under investigation. Okay, then anything else which is surrounding this, anything else that is surrounding the reaction is called the environment or the surrounding. Okay, in this case the cup itself or the beaker itself and everything outside. Okay, is what I'm trying to point out, resonating with everyone. Are we together? Okay, let me ask a question just to prove okay, let me ask a question. What if you've got a reaction like that, then you've got sodium chloride. Let's say there's water here. Let's say there's water, it's immersed in water, like that. is happening in this environment. Now, is the water in this case, is it an environment or a system? The water in this case, is it the environment or the system? So you realize that the water is not, the water in this case is not the point of interest for us. Our point of interest is the reaction itself. So I find that the water in this case, it can't be a system. Okay. Then let's talk about what if we say sodium chloride is being broken to its components. Let's say this sodium chloride, the way we've put it in water, then it's broken down to its component. Let's say sodium, plus chlorine ions. So if this reaction releases energy, meaning the enthalpy of the reaction is going to be negative, right? It has lost energy. We are losing heat. Okay, and this released energy we're just talking about is called the heat. Now, the same heat which is lost, will show a negative, right? We're saying because the heat is lost, so it's negative Q like that. This means that the heat was lost by the sodium chloride. Now, this lost heat will be the same heat that will be gained by the water. The water is a surrounding, right? Okay, so the same heat that has been lost by the sodium chloride, it will be the same heat that will be gained by the water. This all encompasses from the law of conservation of energy. Energy cannot can neither be created made, but it can just be transferred from one form to another. So what do we mean? So meaning the heat that the heat of the reaction itself will just be equals to the heat that the water gained. Okay, so the heat that has been lost by the sodium chloride, it will be the same heat that will be gained by the water in this case. Okay, hope is what I'm talking about is resonating. Then there's what is called you have to also understand what we call heat capacity. Now, what is heat capacity? Okay, what is heat capacity? So heat capacity is just the amount of heat that is required to raise the temperature of a substance by 1 degree Celsius. Okay, let me say this is our substance in here. Let's say it's 36 degrees Celsius, and you want to raise it. Our heat capacity in this case is just be 37 degrees Celsius. So we're just talking about the amount of heat that you are going to, the amount of heat which will be required to raise this temperature of this substance, or the temperature of this substance, from 36 to 37. We're just talking about by 1 degree. That is called heat capacity. Now, this is called heat capacity. Now, there's also what is called specific. There's also what is called specific heat capacity. Okay, now what are we talking about? What is this specific heat capacity? So this is the amount of energy that will be required to raise 1 gram, 1 gram of a substance by 1 degree Celsius. So specific in this case, we're just talking about you've specified the mass. So that's why it's called specific heat capacity. So in this case, if you are going, specific heat capacity is given by the formula. In this case, your energy or your heat energy will just be M. We usually say M cut. Okay, so in this case, this is your energy. Okay, your heat energy. Then this is the mass of the substance, because you've specified the mass. Then this is the specific heat capacity of that substance. Specific heat capacity of that substance. Then our T in this case, this will just be the temperature like that. Okay, so that's what we're talking about. So heat capacity, okay, so now how do you find heat capacity from this expression? Okay, so how are you going to now find the heat capacity from this expression, because this is the expression for energy. Okay, if we made our C in this case the subject of the formula, so what are we going to have? Our specific heat capacity will just be, your Q, which is your heat, over, your mass times the change in temperature, like that. Now you know that your heat or your energy in this case, this is energy, is measured in joules. Okay, then your mass in this case is measured, in what? In kg. Okay, this is multiplied by temperature. Temperature in this case, temperature is measured in Kelvin, but in some instances the mass can also be, grams, depending on the substance that you're talking about, or the circumstance that you're talking about. Okay, now let's also talk about another concept that you need to understand. There's what is called latent heat. Now, what is latent heat? This is the amount of heat which is either absorbed or released during a change of state. In other terms, you can just say it is the heat which is required for a change of state to happen. So latent itself, the word just means this thing is hidden. So you can't see. That's why it's called hidden, because you can't really see when a change of state is happening. It's very hard to see. It's hidden because you're not going to see. So let me say during a a change of state, let me just try to draw a type 1 diagram. If this is our type 1 diagram for change of state, this is our diagram like that. Okay, so at this point, at the change of state, the diagram looks, it looks like this. You can't see that the temperature is rising. You can't see that the temperature maybe is reducing. So at this state, that's where the latent heat will be, and it's very hard. And the temperature doesn't rise to at a change of state. So like that. Okay. Then now this latent heat can either be the latent heat of fusion. Okay. The latent heat of vaporization. Vaporization. Okay, now we're talking about the latent heat of fusion. This is just the amount of heat energy that is required to make a solid become a liquid. To make a solid become a liquid, or a liquid become a solid. For example, if you're moving from a liquid to a solid, in this case the latent heat of fusion will just be the amount of heat energy that will be lost, because you need to lose heat energy from your liquid for it to become a solid like this. Okay, then the other way around, if you're moving from a solid to a liquid, you are going to say that it is the heat which is absorbed. To change a solid to a liquid, you need to absorb the heat in order for those bonds to be broken from the solid so that it becomes a liquid. That would be the latent heat of fusion. Okay, then the latent heat of vaporization is just the heat that is needed to vaporize, just to involve, like you're moving from a liquid. For latent heat of vaporization, you're just moving from a liquid now to a gas. Okay, from a liquid to a gas. So when you're going from a gas to a liquid, it just means that heat will be released. Okay, you need to lose heat from a gas for it to become a solid. Then on the other hand, you need to absorb heat in a liquid for it to become a gas, like that. Okay, so the latent heat of fusion is given by the formula Q, meaning our energy is equals to your mass multiplied by your latent heat of fusion, like that, of F. Then if it's vaporization, where there's F, you put a V, like that. Okay. Now we've talked about a lot. Now let's do some questions. Okay, let's say you've got 100 grams. Let's say you've got 100 grams of water. and you want to raise, the temperature of this 100 grams of water from, let's say the temperature, you're trying to raise it from 20 degrees Celsius, and you want to raise it to 50 degrees Celsius. So now, how much do you need? How much heat do you need? So I'm going to say the specific capacity. You know that the specific capacity for water is a constant, which is 4.184 joule per gram degrees Celsius, like that. So in this case, we're trying to now find the heat. So what will be the heat? We say our heat in this case, we're saying it's M, because it's specific heat capacity, so we specify the mass, right? Okay, M cat. Okay, so in this case, our mass is 100 grams multiplied by 4.184 joules. Okay, this is joules, grams per degrees Celsius. We are multiplying this by our temperature. In this case, we are saying we want to raise it from 20 degrees to 50 degrees. So our change in temperature to be 50 minus 20. Let's say this is degrees. Okay, so now let's solve. What are we going to have? Okay, what can cancel? Your gram and your gram will cancel on this side. Okay, what are we going to also cancel? Your degrees and your degree will cancel, so you're just remaining with joules. Okay, 50 minus 20. Okay, let's say we've got 4 point there's also 100 there, so we've got there's also 4.184 joules. This is multiplied by 100, and this is multiplied by 30. Okay, 30. So this is just your 4.184 joules multiplied by your 3000. Okay, then you can do the calculation. Anyone to just give me a figure? Okay, so you do the calculation. So when you find the answer, it will be just that answer. Let me say that answer, and it will be in what? In joules, like that. Okay, in joules, like that. Let's look at another example. Let's say you have a 70 kg, or let me say a 70 grams of aluminium. Now this 70 grams of aluminium, and this one is at, let's say it's at 180 degrees Celsius. Now you get to drop it in a bucket of water. You get this one and you drop it in a bucket, let's say, or in a beaker, or in a bucket of water, like that. And this is our water, like that. And this water is let's say it's 400 grams. Our water is 400 grams, and it has let's say it has a temperature of let's say 25 degrees Celsius. And in this case, let's say our temperature final, after we've dropped the aluminium into this beaker, our temperature, it moves from 25, it has now gone at 28 degrees Celsius. And we now how do we now calculate the, let's say, the specific heat capacity? Okay, so what are we now going to do? So you know that the specific, okay, the specific heat capacity for water, we know is a specific heat for capacity for water, like we earlier said, it's 4.184 joules per gram degrees Celsius. Okay, now I must mention something before we solve. Look at the temperature difference. Aluminium is hot. It is at 180, like that. Okay, 180 degrees Celsius, and water is just at room temperature, which is 25 degrees Celsius. Okay, 25 degrees Celsius. Now when you drop a hot thing into something that is cold, the cold thing, the temperature rises, right? the whole thing, the temperature drops. That is why you see the temperature is 28 degrees. Our final temperature is 28 degrees. Now the aluminium will be in the water, so they are going to share the same temperature, because the aluminium, if put it in water, they are going to share this same temperature. So the same heat which will be lost by aluminium will be the same heat that will be gained by the water, from the conversation, from our conservation of energy. So what are we saying? We're saying the same heat that will be lost, in this case the same heat that will be lost by the aluminium should be the same heat that should be gained by your water, like that. So we're going to use our law of conservation of energy. Okay, since aluminium is losing heat, so it's negative, so negative m cut. Okay, this should be equals to positive, okay, m cut, like that. Okay, so now let's solve. We're saying negative, the mass for our aluminium is 70, so negative 70 grams. Okay, this is multiplying by your C, because we're trying to find the specific heat capacity for aluminium, then times the change in temperature. So the final temperature was 28 degrees, then the initial temperature for aluminium was 180 degrees Celsius. This, okay, so let's say this is degrees outside. Okay, now this should be equals to the heat for water on the other side. So let's just rub okay, let's just rub here. Okay, let's just rub there. So what are we now going to have? Okay, on the other side here, so what are we going to have? We have positive m, which is for water. For water we said it was 400 grams. This is multiplying by the specific heat capacity of water, which is 4.184 joules per grams degrees Celsius. This is multiplying by the change in temperature. So the temperature for water, we're saying the final temperature was 28 minus the temperature for water that we had put. It was at standard temperature, which was 25 degrees Celsius, like that. So your degrees and the degrees for this side will cancel. Your grams and your grams will cancel. So what are you going to remain with? So if we make C the subject of the formula, in this case, if we make C the subject of the formula, it will just be C. Our C in this case will just be C is equals to, everything this side divided by everything on the other side, right? So we have 400 multiplied by 4.184. This is joules. This is times. When you subtract 28 minus 25, that is 3, right? Okay. So because specific heat capacity is in joules, everything has cancelled. We just remain with joules on top. Divided by, down, we're going to remain with negative 70. Okay. Multiplied by, we've made our C the subject. So multiplied by 28 minus 180. Okay, on my side I'm getting negative 152. This is degrees Celsius. Okay, degrees Celsius, like that. Okay, we're saying this is 70 grams. Okay, so now let's solve. What are we going to have? Okay, okay, on my side I'm getting C to be 0.472. This is joules. There is gram down, so joules per gram per degrees Celsius. So this will be our final answer in this case. Okay, now let's talk about how you find the enthalpy of a reaction. And earlier we said the enthalpy of a reaction When we're introducing the session, we said the enthalpy of a reaction is just the energy that is gained or lost during a change taking place at a constant pressure. So now, how do you find this enthalpy of the reaction? Okay, so we'll solve this. We'll do this using an example. Okay, just to make our work easier. So let's say you've got a reaction NH3. This is a gas. Ammonia is a gas. In this case, it is giving us let's say half N. This is a gas. Okay, plus let's say you have 1. Okay, let's say you have 3/2. Okay, let's say 3/2 of hydrogen molecule. This is a gas. Okay, now let's say the enthalpy that you've been given in this case, the enthalpy of the reaction, let's say the enthalpy of the first reaction, let's say it is equals to, let's say, 46 kilojoules. Okay, now let's then you have another reaction. Let's say not NH, let's say you've got H2. Okay, let's say you put a 2 here. This is grams. This is plus, let's say plus, oxygen molecule. Oxygen is a gas in this case. This is giving us 2 water molecule, 2 water molecules, and water is, in this case, let's say it's in gaseous form. Then let's say the change of the enthalpy in this case for this one, let's say it's a negative 484, let's say, kilojoules. Okay, then let's say they've given us the final reaction, or the desired reaction that we are supposed to find. In this case, they've given us it's 2N, let's say, okay, gas like that, plus let's say 6 water. Okay, this is gas. This is giving you, let's say, 3 oxygen molecule. Okay, oxygen molecule in this case is a gas, plus 4 NH2 like that. Then this is a gas. Okay, now they've given us the enthalpies, the first enthalpy for the reaction and the second enthalpy for the second reaction, but they haven't given us the enthalpy for the final reaction, which we are supposed to find. So now, how are we going to find that enthalpy? The change. So what are we going to do? Okay, what are we going to do? So when you are finding the enthalpy, these are some of the rules that you need to consider. You have to reverse any reactions as needed to give the required reactants and the products. So when you see, like, okay, this one I can reverse it, you can reverse it because you want to at the end you want to get this reaction. So you must struggle with these reactions so that you come up with this reaction. That's what we're talking about. Okay, so let's just do that. So okay, you are going to reverse where necessary as possible. Then you can also multiply the reactions to give the correct numbers of reactants and the products. Okay, and when you reverse your reaction, the enthalpy of the reaction it also changes to the sign changes. If it was positive, it changes to a negative. If it was negative, it changes to a positive. So let's reverse the two reactions. Okay, when we reverse the two reactions, what are we going to have? In this case, let me use a different color. Okay, let me use this one. Okay, when we reverse the reactions, what are we going to have? Let's start with the first one. So our products in this case will become like our reactants. So have N. This is N squared. Okay, I'll remove the states just for space. Okay, this is 3/2. This is H2, and this should give us NH3. So we've reversed the first reaction. And what have we said? When you reverse the reaction, your enthalpy you have to also consider your enthalpy. So in this case, your enthalpy will change. It was positive 46 kilojoules. Now it will be negative 46 kilojoules. Okay, now let's reverse also the second one. We see what we are going to get. When we reverse the second one, what are we going to have? We have 2 water plus, let's say, what are we going to have? You have 2H2 plus O2. Okay, now let's also look at the enthalpy. It is it's negative, so now it will become positive, right? So in this case it will be positive 484 kilojoules, now like that. Okay, now that we found we've reversed, it's what we reverse is it's very far away from the equation that we want to find, this one. So what are we going to do? So we're going to multiply the reactions so that they give us the correct number of reactants and products. Look at the numbers. We've got my halves, we've got, like, let me say, close to decimal. So we're going to multiply these reactions so that we get a proper reaction. So let's just rub on top. We've reversed these ones. Now let's multiply them to get some. Okay, so the first reaction, it's the first reaction in this case. We have we've got half n squared plus 3 2. This is H2. Okay, this is giving us NH3. Okay, and the enthalpy is that. Then the other one, we've got H2O plus 2H2 plus is it plus O2, or it's giving us O2? Okay, so this was giving us O2. So in this case, this is giving us okay, this is giving us O2, like that. It was okay when we reversed it. How did we reverse this one? Okay, so when we reversed the first reaction was let's say H2O was giving us this, actually, not the other way around. So this is positive. Okay, this is positive. So it's the H2O that was giving us this one, because it was the water that was formed in the second reaction. Okay, let's just rub here just to make it okay, this is 3/2. This is H2 here. Okay, so the reaction was H2O. This was giving us, when we reversed it, it was giving us H2 plus O2, like that. Okay, there was a 2 here. Now there's also a 2 here when it was balanced. Okay, now what are we going to do? We're saying we're supposed to multiply these reactions. We're supposed to multiply these reactions by numbers, so that we remove most of these fractions. So we're going to multiply the first one and the second one. Now these ones have got their own enthalpies. This first one, we said it was negative 46 kilojoules. Then the other one was it was positive 484 kilojoules here, like that, in this one. Okay, so now let's say we multiply the first one. Okay, let's say we multiply by 4. Then the one down we multiply by 3. So what are we going to have if we multiply on top by 4? Okay, let's say, what are we going to have when we multiply on top by 4? Okay, let me just keep the reaction that is on top, because that's the reaction that we're supposed to find, the one that is just in white. Okay, So when we multiply on top, what are we going to get? If we multiply 4 multiplied by half, you know, your 2 just divide with the 4, right? So you just remain with the 2. This is N2. This is in gaseous state, okay? Then your 4 multiplied by your 3 over 2. 4 multiplied by 3, that is 12. 12 divided by 2, that is 6. So you have 6H2. Okay, this is giving us your 4 multiplied by your NH3. So you have 4 NH3. So the way we've multiplied through this reaction, you're also going to multiply also your 4 with the enthalpy. Even in this case, you're going to multiply your 3 with your enthalpy. So you multiply 4 multiplied by negative 46. Okay, on my case, it's giving me our enthalpy of change in this case. On my case, is giving me negative 184 kilojoules, like that. Now let's do the second one. 3 multiplied by 2, that is 6. So you have 6 water. Okay, this is giving us your 3 multiplied by your 2 there, that is 6, right? So you've got 6 H2, your 6 H2, okay, plus your 3 multiplied by your oxygen, like that. That will just be your 3 O, your 3O2, like that. Now your change of enthalpy in this case, when you multiply your 3 with 484 kilojoules, okay, I'm getting 1452 kilojoules. Okay, kilojoules, like that. Now what are we now going to do? We can cancel those ones which are common. So like 6 hydrogens and 6 hydrogens will go. So now what are we going to remain? So you realize that on the reactants, we are remaining with 2n squared, which is this one, and this one, which is this one. Okay, we are done on the reactants. Then we're saying it is giving us, what is it giving us? It's giving us on the products. Now we have this one, which is this one, and you know your 3O2, which is with this one. It means we've proved on this one. But now we've just sorted out the reaction. But now let's also sort out the enthalpies. We've got negative 184 kilojoules plus 1452 kilojoules. So if you do a calculation, for me, I'm finding an answer like, you know, this is also positive 1268 kilojoules, like that. Okay, so that is how you find the enthalpy of a reaction. Then there's also what is called the bond enthalpy, although we're not going to spend a lot of time. So this is just the energy that is related in breaking chemical bonds. So the bond enthalpy, breaking those bonds. Energy is required to break bonds, you know that. Energy is also given off in the formation of bonds, you know that. So there's what is called the bond dissociation energy. Now the bond dissociation energy is defined as just the amount of energy that is required to break one more of the covalent bond in a gaseous, let me say, species. If you've got carbon dioxide, and you know, we break the bonds between, you know, carbon and oxygen, the covalent bonds. So what are we going to? We're going to have our carbon and our 2 oxygen, like that. And let's say the energy that was, you know, just for you to break those bonds, let's say the energy that was given is 160, 9 kg. So this is the bond enthalpy. And how do you find the bond? The bond. If they ask you to find the bond of the bond enthalpy of the reaction, so just say, you know, the reaction, the bond energy of the reaction, the bond enthalpy of the reaction. You say, you know, the summation of the bonds, you know, of the one that you have on the reactants minus summation, you know, of the bond enthalpy energies on the products. Okay, so what we're just talking about is just the difference between the energies that are required to break the bonds and that are released in the formation of new ones. Okay, so this is where we end for today. Don't forget to subscribe also to our channel as we are creating more content. See you.